So we talked yesterday about this equation, this E equals mct. That is, the energy that it's going to take to heat something up is going to depend on how much of that thing there is, and this funny little variable called specific heat. Now, what is specific heat is kind of a weird term. And it's kind of a weird concept. It's like, what is it that affects how much energy it's going to take to actually heat something up? If we remember, what is temperature? Temperature is going to be the motion of molecules on a atomic scale. So we've got, if we have a bunch of little water molecules, they're all going to be moving around in random directions, but with some velocity, some speed. And the faster they move, the hotter that thing will feel. So sure, it makes sense to think that, if something's heavier, it would probably take more energy to heat up if there's just physically more of it. But at a microscopic level, I mean, we've already got the amount of something factored in here. At a microscopic level, there are just too many variables to count that could affect how much energy is going to go in to change the temperature of something. For example, something like metal. A metal bar of something takes a very small amount of energy to heat up. The reason for that is that metals tend to have all of these loose electrons floating around. When those electrons get a little bit of energy, they move a lot more. And so it's really easy for energy to move through this whole piece of metal. In the same way, just regular air, just particles whizzing around the atmosphere, just going all over the place. That's pretty easy to heat up, because if I heat up one bit of the air, it's all going to mix up because of convection currents. We already talked about that. So those regular types of heat transfer will affect that. Well, what about water? Well, generally speaking, water molecules made of H2O look kind of like this, and they're really good at really packing in really densely together. So they'll all pack into a system. If I've just got a bunch of water, I'm really going to have a bunch of molecules that look something like this, and they'll all be moving around each other, slamming into each other at colossal speeds. But because they're all packed so closely together, it's actually going to take more energy because it's kind of harder for them to move around as much. Also, these molecules, because of some concepts that we haven't talked about, really like to stick together in a very certain way. And so they're not going to want to move away from each other if they can help it. So there's all these weird little microscopic facts and occurrences that change how much energy it's really going to take to heat something up. And so one of the simplest ideas that goes along with this equation is that how warm or cold does something feel, right? I'll put it this way. Temperature is going to be set. Remember the Zeroth Law of Thermodynamics. The Zeroth Law. Remember, that says that if a few things are at thermal equilibrium with each other, then they're all going to be the same temperature. So if I have a bunch of things sitting in a room at room temperature, let's say that's 70 degrees. 70 degrees Fahrenheit specifically. If everything in that room is just sitting there and it's been sitting there for long enough, then everything in that room is going to be sitting at 70 degrees Fahrenheit. But does everything in a room always feel like it's the same temperature? Try this yourself at home. Just feel things around your house and notice which things feel cold, which things don't feel cold. They're all sitting at the same temperature. But just in my classroom, I've got a meter stick, and I've got just some little bars of aluminum. This aluminum feels much colder than this meter stick does. If I put my hand around this, I put my hand around this, this one feels way colder. This one feels like it could be down to 50 degrees, but it's not. Both of these have been sitting in the same room for the same amount of time, years. Both of them are at the same temperature. If I put these together and took the temperature, I would get the same exact result. So why does this one feel colder? Well, it's because The specific heat for metal is so low. It's so easy for energy to flow through this piece of metal to raise its temperature. So when I grab it with my hand, there is energy flowing from my hand into this block. And because it's much easier for the energy to flow through this, more of the energy moves. So when I hold this block, I'm losing more heat energy than I am when I hold the wooden meter stick. That's why. So just thinking about these things in a certain way, we can kind of see where this specific heat kind of comes from just so many different variables that we just can't account for. And so when we have situations like that in science, that's why we just put together these tables that contain the values that we should use in our equations. Instead of going, well, the water should be like this because the water molecules like to stick together and they're this size and this shape and this density. Those kinds of things, we're just not going to worry about them. It takes so much to think about, and this equation would become so long and unusable that we just go, you know what? I can, I'm just going to figure out what the temperature of this thing is, how much there is, how much energy it took, and then I'll just make a table full of these values. So that's what specific heat is. It's just this quantity that puts together all of these very different concepts at a microscopic level to make it much easier to do calculations.